Okay, so this session is being recorded. So we'll start with the talk. So it is my pleasure to invite Dr. Slavin Pellis from Oak Ridge National Laboratory. Slavin is a senior computational scientist at the lab, and I've had the pleasure to work with him over a number of years now. And he's going to be talking about the work that he's doing on GPUs and power system computation. So over to you, Slavin, and thanks. Looking forward to your talk.
Well, thank you, Shri. Thank you for inviting me to give this talk, and thank you to all of you for attending this webinar. I understand that after years of COVID, people got some fatigue with webinars, and I really appreciate you coming and attending this talk. So I'm going to talk a little bit about next generation computations and modeling for power systems. In this talk, I will touch upon a few aspects of power systems modeling that are going to change with new computational technologies and what that means in particular for us who are working in this area. I'm just trying to, okay. This work has been done within Exascale Computing project, and I acknowledge support received from ASCR and NNSA, as well as support from Oak Ridge Leadership Computing Facility, which provided resources where we could run our computations and tests. There have been lots of people involved in this work. This is the list of people who worked on particular items that I'm going to present today. And without any of these people, this work probably would have never happened. So going back to my mothership, Oak Ridge National Laboratory, we are very proud to host the world's first exascale computer and currently the most powerful supercomputer ever built. Frontier machine produces 1.1 exaflop per second in computational power. So it is marvel of technology and result of many years of dedicated work of researchers from multiple national labs and different vendors. Now, I want to address at the beginning certain myths about exascale computing. So typically when we talk about exascale computing, we talk about world records and pushing the boundaries of getting many, many flops. But actually, what exascale computing means is that your software will perform well on your laptop as well as on a supercomputer. So exascale means scaling up to an exaflop computational power. Not necessarily that you need exaflop computational power to run your computations. Also, another myth that is fairly common in power systems community and elsewhere is, people say, okay, I'm using my, I do all of my work on a workstation. I don't care about parallel computing. This is not my priority. But this is also very misguided view. In my opinion, because today all the computations are done in parallel with certain degree of parallelism. And if you are still signing up to that sequential computing, single thread paradigm, you're actually using only a fraction of the computational power, even if you are using CPU only workstation. Now, why do we care about GPUs and hardware accelerators and heterogeneous computing at all? The reason for that is that in the past, all the computational most of the computational gains, in fact, were achieved by developing faster and finer hardware. So we were able to pack more transistors in a microchip, and we were able to clock these microchips faster and faster. Now we reach these limits. We reach technology limits of traditional semiconductor technology. And right now we need to do more with less. So computers are not getting any faster, microchips are not getting any smaller. The next barrier, next way how to improve computational power is by using fine-grained parallelism at a massive scale. And how does that look in practice? So here is one such example. So we have, so this is a schematic description of a single node on Sierra supercomputer. It's a supercomputer that is similar to Summit at Oak Ridge National Lab. It is based on IBM's Power 9 CPUs. It has these two CPUs here in light blue. And as you can see, there is a non-uniform memory access by these two CPUs because there are some in dark blue shown here, RAM memory blocks here and here that are attached to specific GPUs, and there is an X bus between these two GPUs for communicating data between one and the other. And there are, of course, 4 GPUs with 16 gigabytes of memory each. And they are connected with each other through NV-link connections, as well as connected to CPUs through the same NV links. So the point of showing this internal structure is just to show that it is non-trivial. You don't have a single processing unit. You have, in this case, 6 different processing units. You have non-uniform memory access, and you have different types of memories. And you have to account for all of that when you are designing code that is supposed to run on these machines. Now, what is the main advantage of these machines? If we compare high-end workstation, so this is Intel Core i9 CPU, single CPU. I believe it has 12 cores in there. Peak performance of that machine is somewhere around 220 megaflops. The single Summit node produces 43 teraflops this is actually its peak compute power. And single Frontier node produces a staggering 193 teraflops in computational power. If you compare the size of these machines, I mean physical size of the box, they are comparable. And power supply is slightly bigger. Well, not quite slightly, a good 3 times bigger for Summit and Frontier nodes, but this is not several orders of magnitude bigger. So we are getting several orders of magnitude more performance, but we are using much lower power. So I have this next comparison here for you. If we are to produce same peak performance with traditional CPU technology, it would take about 200 high-end workstations to match the computational power of a single Summit node. So this is IBM's power system AC922. And almost 1,000 of CPU, high-end traditional CPU workstations to produce the same peak power as the single node, single blade of Frontier. And looking at the power consumption, you see if you are using traditional technology to match the power supply needed for Frontier node, which is 2.2 kilowatts, you need half of the megawatt power supply if you are to use traditional technology. So the point of this is that not only that we can generate massive computational power in a supercomputing facility. With GPUs, we can deliver portable computational power. If we have a single GPU or a couple of GPUs on a system, we can deliver portable computational power that can be used for edge computing, that can be deployed at I don't know, control room or on the inverter-based resources for advanced controls and analysis. So this high density of computational power and high computational power per watt of power supply gives us many, many new opportunities. Now, the next argument is if I don't want to do any novel computing and I just want to do things that I've done all the time so far, why do I care about heterogeneous and parallel computing again? And this is very interesting result, actually, which we got just recently. We ran ACOPF, alternating current optimal power flow analysis for 70,000 bus Eastern interconnection synthetic grid model. And we ran exactly the same software using traditional sequential codes. We ran it on Power 9 CPU that has 22 cores, and we ran it on EPIC AMD CPU, which has 64 parallel cores. And what we got is that on 3 times more powerful hardware, we get 2 times slower performance. And we are still investigating the reason for that, so I don't have a hard evidence of what is going on. But what I would guess is that there is less L1 cache accessible to a single process on a processing unit with more cores, and therefore you have more cache misses, and that degrades performance on a processing unit with more CPU cores in this case. So the point that I'm trying to make here is that with hardware technology getting more and more parallel, the traditional methods for analysis that we have used are becoming less and less effective on that hardware, because that hardware is designed for different applications in mind. So even if you want to stay in your domain and not care about parallel computing, it is quite possible that you would see worse performance on new hardware as it gets developed. So next thing is why don't we just simply port everything to GPUs and be done with that and run power systems computations on GPUs, as everyone else is nowadays running computations on GPUs and getting great performances. So this is not very simple, and this is not quite as trivial. In the early days of GPU computing, you would get these reports. We got 200 times speed up running our code on GPUs, or we got 1,000 times speed up. And many of these speed ups were compared to the really poor benchmarks. One good thing that GPU implementations brought to us is that they forced us to rethink how our algorithms were implemented. And simply by rethinking these algorithms, we actually, in many instances in the past, in the legacy software, we were able to remove some poor implementation approaches. But to get a really legitimate head-to-head speed up, that would require a little bit more involved work. And I will try to talk a little bit about these things. But key thing is that power systems have very irregular structure. So unlike in partial differential equations, there are no patterns that you can exploit. And that structure is given by the structure of the power grid. When you are doing partial differential equation analysis, such as computational fluid dynamics, you can adjust your mesh, you can adjust your discretization of the space to suit your computations. In case of power systems, you don't have that flexibility. Power grid is the way how we built it, and we cannot adjust it to suit our computational needs. And another issue is that underlying linear problems are often ill-conditioned, and this is something that hampered our progress quite a bit. So I will just go very quickly through several issues that we have dealt with at exascale computing project, especially ExaSGD sub-project, which is stochastic grid dynamics at exascale. And Shri was, of course, involved in that project, and he was one of the key contributors there. So first things first, let's talk about modeling of power systems. Typically, when you model transmission power grid, the modeling algorithms would loop first over all buses, and then for each bus, the algorithm will loop over everything that is attached to that bus. That creates an execution sequence that is not very favorable for GPUs. And here's the reason why. GPUs operate in warps of 32 threads, and this is for NVIDIA, and AMD GPUs operate in warps, or how they call them, waves, of 64 threads. This means that you have same instruction control sequence for 32 or 64 threads. So all 32 threads have to do the same thing. And in a traditional way of modeling power grids, this almost never happens. So one thing that we did in our project is we reorganized how a model is evaluated. So we put all the buses within one thread warp or within same thread warps, loads within different thread warps, generators, again, different thread warps, lines, and so on and so on. So in that way, we actually avoided what is called a warp divergence. And if we look at the results that we got, these results show that this approach indeed gives us significant speed ups. One thing that I would like to point out on this slide is this figure in the top right corner, and there we are comparing the speed ups of componentized versus traditional approach in modeling power systems. And you can see that we are getting up to 3x speed up when we are using componentized approach on GPUs, whereas on CPUs, on traditional computational technology, we get at par results for most of the times. So this is actually an evidence, and this was all obtained in a proxy app before we actually even implemented that in a real modeling system. But this confirmed what we have suspected from the beginning, that different modeling strategy is more appropriate when using GPUs. So how does that impact your modeling tool? Well, the solution is fairly simple when you know what to look for. You read your data, you actually transform that data and create data structures that are that allow you for efficient single instruction multiple data layout, or SIMD, and then you solve this problem on GPU. And this was all implemented in Hexago, and Shri is the lead developer of that software package. So this is actually entire modeling framework for power systems simulations. And we were able to get quite good performance on GPUs with that modeling framework. And you can learn more about Hexago simply by Googling for it. All the documentation and the software is available as an open source. Another bigger problem, and this was a major bottleneck, was how to solve underlying sparse linear systems on GPUs. And as you can see, this is the summary of the results published in a paper by Kasia Šviridović, where we analyzed the performance of different GPU-enabled linear solvers. So whenever we are doing optimal power flow analysis or dynamic simulations, what we end up doing is solving a sequence of linear systems. Now, these linear systems are extremely ill-conditioned and very difficult to solve even on CPUs. On GPUs, we have some additional constraints that we have to deal with. And with these constraints, it is really difficult to get the advantage of high computational power of GPUs. And as you can see in this table is that CPU-only reference, MA57, the solver that's been around for good 20 years or more now, is outperforming many other GPU competitors. And what we found is, in collaboration with the NVIDIA developers, that a different approach where we use refactorization actually gives us first meaningful speed up over the CPU reference. Now, all of these other GPU-enabled linear solvers work well in their own domains, but for power systems, they perform really poorly. So what was the challenge there? If you look at the sequence or process flow of solving the linear system, it always starts with some reordering, symbolic factorization, then numeric factorization follows, and then you have triangular solve, and eventually iterative refinement. Now, reordering, symbolic factorization, and numeric factorization, if you have pivoting, is a process that, again, same as in the case of modeling, causes a lot of warp divergence. You cannot create these SIMD blocks of instructions. So what you are left with is triangular solve, which is by itself not quite easy to parallelize, but you can port it to GPUs and iterative refinement that yield that fine-grained parallelism. The good thing here is, though, that you are performing this linear solve several times. And in typical ACOPF, there are several hundred of these linear solves, and each of these linear solves has the same sparsity pattern. So once you do numerical factorization, you can copy the permutation vectors, and you can store the sparse L and U factors. And instead of going through numerical factorization and pivoting every time, you can actually reuse the factors and permutation vectors at every next iteration, and use only refactorization with static pivoting. What that means that you can do first solve using KLU or some of these proven CPU solvers, and then for every next iteration, you're actually running computations on GPU in a way that is suitable for GPUs. That first iteration cost will be amortized over hundreds of subsequent iterations. The reason why this works is because we have effective iterative refinement that can restore the accuracy of the solution that gets degraded when you use this refactorization. On CPUs, this is not a big deal because numerical factorization and pivoting is not as expensive as on GPUs. But on GPUs, we have to think a little bit differently. And if we compare the results, so these are the two, on the left hand side, these are the two results from MA57 on two different CPUs. And then we have four different test cases, two of them with Q Solver by NVIDIA, another two by that are obtained in collaboration with Ginkgo team. So this is Karlsruhe Institute of Technology and then University of Tennessee in Knoxville. And we have like four different techniques that we can apply, and each one of them beats the best baseline result on CPU. So this is still very much work in progress, but we have a quite clear technical path how to develop effective linear solvers on GPUs for ill-conditioned systems such as those arising in power systems analysis. And I believe I don't have that much time to go into the depths of other items that I wanted to talk about today, but let me just briefly mention different programming models for GPU. So if you really want to create code for NVIDIA GPUs or AMD GPUs, you need to understand vendor-specific programming languages. In this case, this is CUDA, or Compute Unified Device Architecture language, or Heterogeneous Compute Interface for Portability, or HIP, which is the language used to program on AMD GPUs. Both of these languages are fairly similar to each other, but are also not very friendly to use. In our project, we used portability layers or portability libraries. And these libraries, the libraries that we selected are Ampere and Raja. Ampere is managing memory allocations and memory transfers, and Raja is managing parallelization of for loops. As you can see, these portability libraries add some coding overhead, if you will, but they essentially allow you to write the same code as you would write it in C++ or C, but with a little bit of a twist. So for us, it sped up development significantly because we were able to do minor modifications to the CPU code and port it to GPU by simply wrapping these bodies of our for loops in these Raja loops. So for whoever is interested in learning more about Raja, Ampere, and other portability libraries such as Cocos, I would be happy to direct you to the proper resources. I'm going to skip over quite a bit of work and just go to the summary slide because I'm running out of time here. But what I would like you to take from this talk is that heterogeneous computing is presenting us with unprecedented computational power, but there is no easy way to use it. So it will require a little bit of rethinking of both implementation and mathematical algorithms that we need to use when running power systems applications. Again, the value of heterogeneous computing is not necessarily only in supercomputing or extreme computing cases, but it also provides high density computational power that is portable and that can be integrated with control devices that can be deployed in a field or that can be used in a control room, if you will. And another thing that is important to note is that you don't need to do everything all by yourself. There are lots of software already available. There are portability libraries. There are optimization packages that are threaded, and modeling environments such as Hexago that have been developed. So far, we scratched only the surface of power system modeling for heterogeneous platforms, but we have a very good idea how to move this research forward. And with that, I will just present some of the key software that has been used in this project. And I would thank you for your attention and open for any questions that you might have.
Thank you very much, Slavin. I think this was, a very insightful presentation on, so many aspects of GPUs, supercomputers, the libraries, programming models, and all that is needed on GPUs. We have questions. I think I see a hand raised by Anas. So if you can unmute yourself and ask the question.
Sure. Thank you very much for the exciting and very good presentation. I do have a question regarding the slide that's titled Sparse Direct Solver Workflow that shows the KLU comparison with other solvers. You mentioned that in order to get effective GPU parallelization, we can do the pivoting and the numeric permutation once at the beginning, and then reuse the same reordering in the subsequent iterations. But in real-time applications and real-time grids, we have nonlinear elements and we have a lot of switching. Sometimes the pivot changes. So we are, in order to keep the accuracy of the solution, we are forced to redo the pivot order and recompute the numeric permutation and recompute L and U all over again without using refactorization. We use full factorization. Now, in this case, what's your recommendation? Is the GPU parallelization still going to be effective?
So the question is, actually, if you have switch, does your sparsity pattern changes?
Exactly.
Change.
Exactly.
If your sparsity pattern change, you do need to do full factorization with pivoting and save new L and U sparse factors and the same permutation vectors. However, in that case, you would still need a couple of hundred iterations till you converge to a solution of the nonlinear system. So you would still be able to amortize the cost of that full factorization, numerical factorization, over the subsequent iteration. So this is the idea.
Okay. Another question I have is regarding the hardware. When we use CPU parallelization, and especially if we're dealing with commercial software, most of the users now have laptops with like i5, i7, so they have the hardware or the CPU disposal on their machines. So it's easier to run on CPUs compared to GPU. How advanced now the GPU like chips spread in like usual laptops?
So again, all of this software will run efficiently on your laptop as well as on a supercomputer. And the point of this is that if you have access to powerful GPUs or multi-core CPU, then you would be able to use your hardware resources far more efficiently than you would if you are using more traditional sequential algorithms. One GPU resource that could be utilized are gaming GPUs, which are still programmable. They are not as powerful as V100, Volta 100 that is used in Summit supercomputer, for example, but they are much cheaper and more accessible.
Okay.
So you have a big spectrum of different fine-grained parallel devices that you can use with these techniques.
Okay, thank you.
I see we have another question. Amro, if you can unmute yourself and ask your question.
Hi, you hear me?
Yes.
We can hear you.
Thank you for your presentation. I have actually many questions, but I will only ask two to keep the time for others. How big is the system that you are using? So is there like a general key point when we go to the parallelization and when we don't go to the parallelization? For example, if you have like a small system, can you still using the GPU will gain?
Well, that's an excellent question. So for power grids of a couple of thousand buses, you are pretty much at par whether you are using CPUs or GPUs. For 10,000 buses and more, you would most likely see significant acceleration when using GPUs.
Okay. So it does related also to the complexity of the system or only related to the buses?
It is related to both. Actually, I think the instances where you want to use GPUs are instances where you have lots of computations to do. So the larger your system is, the more advantage you will take. The more advantages you will get by using GPUs or any other fine-grained parallel technique.
Okay. The second question is, what is the key point to parallelize the system? Like the matrix itself, you can like separate between the sub matrices, or how you parallelize actually in terms of our system?
So there are two things for two parts to the answer to that question. First of all, the computational cost of ACOPF, AC optimal power flow analysis, about 60% of the overall computational cost is within solving the underlying linear system. So most of the effort that we put in this project was in finding efficient ways to solve these underlying linear systems that we discussed. As for the model evaluation, which takes about 30% of the overall time, so this is the next largest cost, the trick is to implement a component-wise modeling approach so that you group all the components that are same, that are executing same mathematics, to group them within same warps, thread warps. And the other very important aspect is that these components that are grouped within the same warp, that they are operating on data that is nearby in memory, so that you can move the entire data needed for that warp into the L1 cache. So that requires a little bit of computational science and domain expertise to get it to work. And this is why you need people like Shri and many others who contributed to this project, who can interface with different skills and with different scientists and researchers. Once you implement these algorithms in a tool such as Hexago, then from user point of view, it is fairly easy to use these because these things are hidden from the user. But to get these algorithms and to tune them to be efficient, that requires interdisciplinary work.
Great. You know, like there are so many packages for using the GPU. From your experience, do you recommend some of them that they may propose lower latency or overhead?
So I think before answering the question, let me just, in the interest of time, maybe this is the last question, Slavin, you can answer. And then Amro, feel free to, put any other questions that you have in the chat. And then Slavin, if you could, take a look at the chat and answer it, that'll be great.
Yeah,
Sorry
sure.
for the interruption. Go ahead.
Thank you very much.
To answer the last question, or
yes, please.
Okay.
Yeah.
So what do you mean by packages?
Because for me, for example, if I want to use like parallelization, I use like a certain package, for example, OpenMB for the CPU, right? But there's still others. So for the GPU, it could like apply the same methodology. There's many packages like CUDA package and so on.
So my advice would be use whatever is most whatever you find it easiest to learn. And as soon as you start with one package, it would be relatively low effort to move to the other package. But what we use in our projects were these portability libraries, Ampere and Raja. Similar approach is implemented by Cocos, but my recommendation would be start with Raja.
Thank you very much.
All right, thank you for the questions, and thank you, Slaven, once again for that exciting presentation. If you have anyone else has questions, please feel free to put the questions in the chat box, and I can monitor them. Or for Slaven, if you can take a look at the questions.
Sure.
So we'll move to our second presenter. Our second presenter is Professor Jin Xu. Jin, are you online?
Yeah, I'm here.
Okay, great. So if you could share your slides, I'll quickly introduce you, and then you can get started with your presentation. So let's see. Okay, great. So I just want to confirm that we can see your slides. So thank you, Jin. Our second presenter is Professor Jin Xu from Shanghai Jiaotong University. And he's going to be talking about some of the work that he's doing on modeling and simulation of MMC systems and power electronics. And I'm really looking forward to this talk because one of the key areas right now in power grids is on power electronics modeling and simulation. And over to you, Jin.
Thank you, Shui. And thank you for attending this webinar. I'm Xu Jing from Shanghai Jiaotong University. I have been working on the research and the development of the real-time simulation of power systems integrated with power electronics for several years. And today, I will give a report about our recent works, which is about the modeling and the real-time simulation of the high-frequency and cascaded power electronic systems. First, I will give a brief introduction about the background and challenges of today's real-time simulation of power systems. Then, I will introduce the three parts of our recent works. The part one is about an EMTP solver. We call it the compact EMTP solver or CEMTP solver, which is designed for the FPGA-based simulator, but we believe it can also be applied in a GPU-based platform. The part two is about a generic equivalent modeling method. With this method, the simulator can automatically build an equivalent model of most cascaded PE devices, including the cascaded DAB and the SST, and of course, including the traditional MMC. The part three is about a portal analysis method, which is a circuit solution method designed for the complicated power electronic circuits. And as we know, the power electronics have been widely used in the power systems and brings great challenges to our to the real-time simulation of power systems. And first, the high penetration of power electronic devices lead to the high order of power system model, and that will greatly influence the simulation efficiencies and limit the system scales of simulation, real-time simulation. And second is the topologies of PE devices are more diversified, which brings great difficulties to the model development for both simulator manufacturers and the simulation users. Third, many PE devices have a high switching frequency over 10 kHz, such as the dual active bridge, abbreviated as DAB. The high switching frequencies requires small time steps of the simulation, and that may also cause numerical oscillations. Besides, there are still many challenges not mentioned here, such as the black box problem of the PE devices controllers. An example of the mentioned challenges is the application of cascaded PE devices, such as the modular multi-level converter, abbreviated as MMC. MMC is often used in the flexible HVDC systems for example, for the renewable energy collections and the transmissions. In the past 10 years, the flexible HVDC technologies are faster developed and more applied in the power system of China. The transmitting power project have been increased by over 400 times from about 18 million watts to 8,000 million watts. The submodules number per station has been increased by over 15 times, from about over 300 to about over 5,000, which means each valve have over 800 submodules. That great number of submodules will also cause great computation burden without equivalent modeling. Apart from the MMC, there are also many applications of new topologies of cascaded power electronic devices, such as the power electronic transformers, or also we call it the solid state transformers. The submodule of PET are more complicated than those of the MMC, including the dual active bridge, abbreviated as DAB, and the single active bridge, cascaded H bridge DAB, and multi-active bridge. The cascading styles of these submodules are also more diversified than those of MMC, including the input in series, output in parallel, and input in parallel, output in series, and the input in series and output in the series, and the input in parallel and output in parallel. The diversified topologies of the PET brings great difficulty to the development of the corresponding equivalent models for both the simulation manufacturer and the simulation users. And as we may know, the equivalent models of MMC is well developed and embedded in most real-time simulators, such as RTDS's Novel Core and the Oppo RT's RTLab. Both these simulators support up to 1,000 submodules per valve, namely over 6,000 submodules in a single stations. The submodules can be the half bridge, the full bridge, and the clamp diode type, and or the 3-level NPC type. That means the MMC consisting of the other submodules not included here cannot be simulated with the embedded models. The other cascaded power electronic devices, such as PET, are not included in the above embedded equivalent model library. So it requires the simulation users to build their PET model with the component of half bridge, full bridge, or even with the basic component of IGBT models. And in the real-time simulator of RTDS, for example, this user build model will be solved by the generic power electronic solvers. This solver can simulate the PE devices of arbitrary configurations at a very small time step, as small as over 200 nanoseconds. But it will also limit the circuit size to no more than about 300 switches, namely no more than 22 half-bridges submodules per worth of MMC. That's only 1/50 of the embedded equivalent MMC models. So the development of the new cascaded PE models is very important, and considering the diversity of the PE topologies, a generic equivalent modeling method is required. A few years ago, we focused on how to model PE devices accurately with the basic components and the PE switches models. We proposed a generalized associated discrete circuit model, abbreviated as the GADC model. So the power converter model with this switch model is more accurate than that of the traditional LC model in the FPGA-based real-time simulator. In recent years, we focused more on how to model cascaded PE devices efficiently with more generic equivalent method. First, a compact EMTP solver is proposed, and this solver has few steps in one simulation loop and can reduce the time cost. So the small time step of the simulation is allowed, and the switching time of the high frequency PE devices can be accurately captured. This software is designed for FPGA, and we will going to apply it in the GPU-based platform. And in 2022, we proposed the generic equivalent modeling method for cascaded N-port PE devices and the portal-based circuit solution algorithms. Both of them were introduced later. So the next part is about the proposed compact EMTP solver. A few years ago, we were developing an FPGA-based simulator, and we were going to simulate 50 kilohertz PET. A small time step, about 200 nanoseconds, is required, but it's very difficult to complete a simulation loop in such a small time step. So the first problem we are going to solve is how to design a FPGA-based EMTP solver which can complete the simulation loop with a shorter time. The traditional EMTP solver complete many calculation steps in sequence. The large time cost requires a large time step in the real-time simulation. That brings inaccuracy for the high-frequency switching PE devices. So we derived the process of the EMTP simulation loop and designed a compact EMTP solver for the FPGA-based real-time simulation. We first applied the traditional EMTP solver on the FPGA. This solver complete these calculation steps in sequence. First is the computing the history currents according to the branch voltage and branch currents of last simulation step, and then is the computing of the nodal injection currents, and then computing nodal voltages, and finally computing the branch voltages and branch currents. This software completes one simulation loop over about 200 tickets. The clocking frequency of the FPGA we use is about 130 million hertz. So the one simulation loop costs over 1.2 to 5 microseconds. That's not small enough for the high-frequency power electronic simulation, such as the solid-state transformer. So we design a compact EMTP solver. Some calculation steps in the traditional EMTP solvers are merged in the compact EMTP solver. As a result, there are only 2 steps left. The first step is the calculation of the history current, and the second step is the calculation of the nodal voltages and the branch currents. The calculation of the history currents can be seen as the update of the state variables, and the calculation of the other voltages or the other currents can be seen as the update of the output variables. As there are only 2 steps in sequence, the compact EMTP solvers complete one simulation step in less than 40 tickets, which means the one simulation step only costs less than 200 nanoseconds. That's enough for the over 50 kilohertz switching frequency. And the entire simulation loop of the compact EMTP solver is displayed in these figures. And the computation task in a simulation loop can be classified into the state variable updates and the output variable updates. This task consists of general metric vector multiplications and also the diagonal matrix multiplications and some logic operations for the switch state check. And in this paper, there is more evident. It's more evident that the most computation tasks can be executed in parallel. Besides, in each matrix vector multiplications, parallelized element operation can be designed to decrease the computation time further. This compact EMTP solver is implied on an NIPXI platform. The circuit data is arranged in a specific platform in TXT file, and then it is parsed by a self-developed LabVIEW script, and then it's transformed is the matrix, the coefficient matrix pre-stored, and it was passed to the compact EMTP solver in the LabVIEW script form, and then it's compiled and downloaded on the FPGA. Here is the real-time simulation result of PET, and the results are also compared with the hardware experiment result. The switch frequency is defined as 50 kilohertz, and the time step is selected as 250 nanoseconds. And the simulation results are almost very close to the experiment result. And the next part is about the generic equivalent modeling method. The second problem we met is how to simulate the cascaded PE devices efficiently, and as it may consist of N-port submodules with arbitrary topologies. The mainstream real-time simulator only include equivalent models of MMC, consisting of only the single-port submodules, such as the half-bridged, full-bridged, and etc. And the cascaded PE devices, such as the PET, consisting of the 2-port or more port submodules, and they had to be simulated with the detailed models at a low efficiency. So in this part, we will introduce the generic equivalent modeling method for the cascaded N-port PE devices, which can help the researchers to get a simulation model of cascaded PE devices with arbitrary topologies. First, I will give a brief review on the traditional equivalent model of the MMC, which is adopted in the mainstream real-time simulators. The embedded model of MMC are based on the ARM equivalent model proposed by Professor A.M. Goley. This modeling method derived an equivalent model of each arm in the MMC. The arm with n submodules and n plus 1 nodes is equivalent to 7 circuits with only 2 nodes. This greatly reduces the order of the MMC models and thus improves the simulation efficiencies. But this modeling method is limited to the single port SM with the several common SM topologies, such as the half bridge and full bridge and etc. And the cascading style of the submodules is also limited to the series connections. So we propose the generic equivalent modeling method. In this method, the inductor or the other basic components can be treated as a single port component, and of course the half bridge or the full bridge circuit can also be seen as a single port component. As for the DAB circuit, it can be seen as a 2-port component. Both the single port component and the 2-port component are derived into the discrete state space models as shown on the left buttons. These models can be seen as a matrix version of the traditional companion circuit models. The size of the vector IH is determined by the number of the dynamic components included in these components. And the size of I port and the U port are determined by the number of the ports. And the coefficiency matrix A, B, C, D will be changed as the switch state changes of the each component. This discrete state space modeling method can be generalized to the N-port submodule with arbitrary topologies. And on the left buttons list how to pre-calculate the 4 matrix ABCDs. All these matrices can be obtained by from the topological information and the component parameters. So these matrices are pre-calculated and pre-stored before the simulation loop starts. In the simulation loop, the matrix ABCD are loaded from the memory according to the switch state inside the submodules. As for the cascaded submodules, they are equivalently modeled with this discrete state space model for a second time, and the traditional equivalent model of MMC can be seen as a special case of the proposed equivalent model with the port number is only 1. And this equivalent model is compatible with the traditional EMTP solvers, which is only needed to be slightly modified. The equivalent model of CHB DAB based PET is tested in the both the real-time simulation and the offline simulations. This PET is cascaded PE devices consisting of the 2-port submodules of the DAB of the CHB DAB. In the offline simulation, the equivalent model is tested and compared with the detailed model. The waveform are almost the same, And in the real-time simulation, a mid-range performance FPGA is adopted. It can support up to 42 CHB-DAB submodules, namely 630 components. Simulation scale is increased by about 10 times compared with the detailed models we used, we tested here. The equivalent model of MMC-based PET is also tested. This PET is cascaded PET devices consisting of four-port submodules. From the AC side, this PET can be seen as MMC, but the submodule capacitors voltage are maintained by a low voltage DC bus. These submodules are more complicated than before. It has 4 ports and 3 in series connections and 1 in parallel connections. The waveform of the equivalent models and the detailed models are still almost the same, and the speed up ratio of the equivalent model range from 1.32 times to 7 times when the number of the submodules increase. The next part is about the portal analysis method. In the modeling of the cascaded DAB, we find the input current from one node is equal to the output current from the other node of the same port. That means the information of the nodal voltage equations is redundant. So we propose a portal analysis method for the EMT simulations of PETs instead of the traditional nodal analysis method. The basic idea of the portal analysis method is to establish the portal voltage equations instead of the nodal voltage equations. In the nodal analysis method, a branch usually has 2 nodes, and the network is constructed with branches. But in the portal analysis method, a component can have 1 or more ports. These components here can be referred to the submodules in the last part, or just the basic ILC components, and the network is constructed with this component. Nodal is no longer the basic element in the portal analysis and becomes the part of the port. Here gives some basic components in the portal analysis, such as the ILC components and the 2-wind transformer and the 4-bridge. The left column shows the portal equations of these components. For the basic ILC components, the portal equations may be even complex than the nodal equations, but for the more complicated components, such as the 4-bridge circuit, the portal equations has smaller orders of model than the nodal equations. In the nodal analysis, the 4-bridge has 4 orders, but in the portal analysis, it has only two orders. The history current expressions of these basic components are the same with those in the nodal analysis, only related to the parameters and the integration method. Here gives an example of the cascaded DAB. On the right is the portal voltage equations, from which we can find the following features. The portal admittance matrix YP is very sparse and diagonally dominant and shows a band-like characteristics. The argumented part Q only consists of 1 or -1 and 0, and it's very similar to the nodal admittance matrix, but it has less orders. The traditional EMT simulation algorithms only need to be slightly modified for the portal analysis. The order of the voltage equations is reduced compared with the nodal analysis. The order of the voltage equations is reduced because the redundant informations of the portal currents are reduced. And due to the port tiering method, the components are highly decoupled and the YP is partitioned. And YP, as we have mentioned, the YP is diagonally dominant and shows a band-like characteristic. And the sparse YP can be stored as two vectors. Due to the usage of the dichotic algorithms and the Thomas algorithms in our simulation test, the speed of solving the portal and voltage equations can also be greatly improved as we can do in the nodal analysis method. Here is a DC-DC PETs, namely DC transformer with 10 cascaded DAB is simulated with the portal analysis method at a time step of 5 microseconds, and the accuracy is tested by comparing with the result of the Piscata EMTDC. And besides, the efficiency is also tested. We use two different algorithms to solve the algorithm to solve the portal voltage equations, including the dichotics algorithms and the Thomas algorithms. By comparing with the time cost of the PCAT, the efficiency of the portal analysis method proved to be higher, and no matter the voltage equations is solved by which algorithms. So finally, here is the summary of our recent works. The first is about, as we have introduced before, is about the FPGA-based EMTP solver we call the compact EMTP solvers. And then we proposed the generic equivalent modeling method, which can automatically build up cascaded N-port submodules of arbitrary topologies. And finally, we introduced the N-port, the portal analysis method instead of the traditional nodal analysis method. And that's all the things I want to share with you today. And thank you for listening, and I'm here for any questions. Yeah.
Thank you very much. I think this was a very interesting presentation on different aspects of power electronics modeling and simulation, including FPGA and the port analysis method that you introduce, and other aspects as well. I see questions on the chat. Also, I would if anyone has questions, please raise your hands, and I'll get you for questions on questions related. So the first question we have is from Slaven. He's asking, for your power electronic simulations on FPGA, are you using piecewise linear or discretized nonlinear models? Also, what is the numerical integration scheme you're using? Slaven, do you want to expand on that, or?
I think you covered it really well. This was my question in essence.
Okay.
Okay. The model we used on FPGA are piecewise linear models, and it's no matter which numerical integration scheme. It can be backward Euler method and all the other integration method. All of them can be used, but the switch models are piecewise linear models.
Okay, thanks.
Thank you.
Thank you, Slaven. We have a question from Amro. If you can unmute yourself and ask the question.
Thank you, Shu, for your presentation. I will start from the last slides. You mentioned in the simulation algorithm based on PAM that the sparse YP can be stored as 2 vectors. Usually the sparse matrix can be stored in 3 vectors, the column rows, the values, and the column indices. So why only 2 vectors?
Sorry, I didn't quite get your questions. Can you?
Okay, so here you mentioned in the point number 3 in the last sentence that the sparse YP can be stored as 2 vectors. Usually, as far as I know, that the sparse matrix has to be stored on 3 vectors.
Oh, yes. Sorry, it's a typo. Yes. The
Okay.
sparse YP are stored as 3 vectors. Yes.
Okay. So the hardware that you are using is FPGA, which is are taking the control signal from the lab view. True?
Yeah. Yes. The platform we use is now based on an NI platform, and there are FPGA modules here and plug into these clusters. And
So
yeah.
So the real system is it's taken from the laptop, or there is a real system?
You mean the laptop?
Yes, because here I can see in the host section in the flowchart below
No.
that the first step is
Okay.
a circuit data file.
The real-time systems are on the CPUs of the IPX platform and the FPGA, not on the host PC. The host PC is just served as the observer, and we can observe the waveform from the host PC, or we can design a circuit and download to the platform. But the host PC is not a real-time systems.
But all the systems are in the national instrument, right?
Yes.
In the NI, right?
Yes.
So it's a
the
hardware
moment,
in loop. So it's
it's hardware
right.
in loop, and here is the real controllers with connected with the FPGA, so the I/O connectors.
Okay. You mentioned that you have like many station that you are testing. So what's the station that you test in your system? It's a real one, or you made the system by yourself? Like the power system?
We test with the real assistance is PET. Is real assistant. It's compared with the real-time simulation, and the others made designed by ourselves, and not the real system.
Okay. Thank you very much.
Thank you.
Thank you for that question. So I have I have a question on the port analysis method. I thought that was very interesting. Is that it seems to me that it's the same equations. It's just the reworking of the equations instead of the nodal analysis method. What you're doing is kind of and let me know if this is correct. It's kind of like restructuring the equations in some way, so that instead of the node equations, now you have the components described by the port equations. So in the end, the equations are the same. It's just the restructuring of them. Is that right?
Yes, it's as we were developing, we were trying to establish the nodal voltage equations of DC-DC conversion systems. So we find the current from one node of one port is equal to the other current of the node of the same port. So we found that the information is reductant, and so we try to reduce the voltage equations by use the portal currents and the portal voltages instead of the nodal voltages and the injection current. So we reconstructed the voltage equations with YP, VP, and the IP, namely the portal voltage equations. And but we also found it's very For the time being, it's very limited to the DC-DC systems. Not it's not it cannot for the moment it cannot be applied to the three-phase systems. As for the three-phase systems, there is no such portal features like the DC-DC systems.
Okay, thank you. One other question that I had was on the speed up that you showed, and you did a comparison between PSCAD and dioptics. Was PSCAD run in parallel over here? Because my understanding is probably PSCAD is running just on one CPU, whereas the dioptics is kind of parallelizing it across a number of cores.
Sorry, I can't catch you clearly.
Sorry, so in the dioptics method, you are partitioning your
Yes.
your equations or your network, and are you solving them in parallel using multi-core or something like that? Or is that just done on one CPU and that's what the speed up that you gain as when you compare it with PSCAD?
Okay, it's just only one CPU core, and it's not a design deployed on multi cores.
Okay. Okay. All right. I see there's probably another question on the chat. So let's see. So Amar, do you want to unmute yourself and ask your question?
Yes, I mean, if there's no question from other people, I have questions.
Sorry, Amro, I was referring to Amar Sagar.
Okay.
Yes, I'm here. Yeah, sorry.
Yeah.
Thanks, Shri. Yeah, just a quick question. Thank you. Great presentation, Chin. Are you using any sparse solvers in your slide 12? You have an equation where you have to linear solve the system, right? So, are you using any of that concepts like KLU solver, or are you doing a dense solve methods?
Sorry, the connection is not very stable, and I didn't quite get your question.
In slide 12, did you
Slide
use
12?
slide 12?
Okay.
Yeah, so here.
Yeah.
So you have the y in this step 2. There are
Yeah.
these matrix inverses or the matrix solves, right? So this K and L. Did you
Yeah.
actually are they sparse matrices similar to what Slaven was talking about, or are they full matrices?
Okay. You mentioned a very important point. The K and L matrix are not sparse matrix, and so the compact EMTP solvers will not use the sparse technology. It's just for the for us for is very suitable for the small power electronic systems, as it will break the sparse characteristics of the original systems. So, and we think the compact EMTP solver is suitable for FPGA, also is based on the consideration that the sparse technologies designed on FPGA will cost many resources. So we designed this software not based on the sparse technologies.
Sure. Thank you.
Mm-hmm.
Thank you, Amar, for that question. So we'll take two last questions, one from Slavin, which he has put in the chat box, and another one from Amro. So Slavin, your question is, I think it's a very fundamental question that you're asking over here is in your comparison of nodal analysis versus port analysis, what is the difference between a node and a port?
Okay. The node has only one node, and the pod may has two node, and not two nodes consist not any two nodes will be a pod. Only the current injected into one node and the output from the other, the input current and output current are equivalent, equal. These two nodes can be called pod.
Okay, I'm not quite sure
So-
that I understood that, but if you have a reference or paper where you explain that in more detail,
Okay.
I would be delighted to read that and learn more about it.
Yeah, I'm glad to send you our paper, but it's still in press and we will
Oh, I
give
see.
you. Okay.
All right, so let's go to Amro for one last quick question. Amro.
Thank you very much. It's a continue to the just the question that has been raised now. If we go please to the slides that shows the pacing components in PAM.
Okay. So, a minute.
Yes, exactly this one. So you mentioned that PAM will find the reductance of the equation, but as I can see here from this like figures that you like for example, how we can find the current in G1 because we cannot with this PAM we cannot find it, right?
Yeah.
Like if we go to the full bridge, if we go to the full bridge figure on
Yeah.
the, yes. So here when we make the matrices, so I can see we can find the VP1 and VP2, right? And
Yeah.
which those belongs to the port. But if we say like I want to find the G1, how can I find it? The VG1.
Visual. Sorry, I can't just get.
So this is the voltage on the resistance or of J1. So what I mean is here, when we go to PAM, we cannot find like nodes or current for some of the elements, right?
Yeah.
So it's kind of like aggregated model rather
Yeah.
than to calculate for everyone for every component, then we can take it as a package, right?
Yes.
Okay. Okay. Thank you very much.
Yeah.
All right. So I think we are just about a minute over. So first of all, I want to thank Slavin and Jin for their excellent presentation. So, thank you so much for, all the insights that you presented to us. And I want to thank everyone who has attended. As I mentioned, if you've not done already, please add your email address to the chat so that, we can send you the slides for this webinar as well as the recording. We are recording this webinar. And with that, I'd like to conclude and thank you so much for attending and have a nice rest of the day. Take care.
Thank you for organizing, Shri.
Sure thing.
Thank you all.
Thank you very much. Goodbye.